Hello everyone. Today I'm going to cover probably the most important abstraction Stl.Fusion has. I computed of T, and again I'm going to run the tutorial and go to part 2 of it. That's the part I'm going to talk about. And um, as it was done previously, I'll run all the samples or like most of the samples from this part in separate dedicated console app we are going to create right now. It okay. Earlier I explained you how to create services that compute everything just once and recompute their values only when their dependencies change. And that's one of key features Fusion offers. But today we are going to talk about the abstraction that kind of backs all of this and helps to implement this behavior. It's called iComputed, and it's an interface, but there is a base class as well that implements this interface and a few uh, descendants of this base class. So what's unique about iComputed in Fusion and let's say similar abstractions in other frameworks like MobX or Cow? First of all, this type is almost immutable. Almost means the only thing that happens with it during its lifetime is state change. When you create a new instance, usually you get an instance in computing state. Once it gets its value, it becomes consistent. And at this moment, it basically becomes almost immutable. And the only thing that may happen later with it is transitioning to inconsistent state. And that's basically it. Besides that, you can add event handlers at any moment, but and add dependencies while the state is computing. And that's basically it. In every other sense, it's an immutable object. So everything, I mean, every computation Fusion supports is supposed to be asynchronous. You can run synchronous computations using synchronous basically tasks as well, but ultimately everything is crafted for in assumption that computations are asynchronous. I computed and its implementations are completely thread safe. And I think that's the biggest difference with like most of other frameworks. I mean, thread safety and immutability. Uh, Basically, this allows to use this abstraction on the server side. And what else? Oh, and one other important part. If you look at, for example, MobX, you will quickly discover that, or at least like maybe I didn't look or like dig too deeply, but it feels like there is no concept like invalidation in most of these frameworks. Usually they presume that if something or like if one of dependencies was changed, then like you should immediately recompute the whatever is dependent. And Fusion completely separates these two things. This part of the tutorial explains why this makes sense, and it's like the description is provided in the very end. But overall, that's how it works. So it's also a transparent abstraction in Fusion in the sense that you mostly don't deal with iComputed directly. And interestingly, it's also GC friendly. Okay, let's ignore this part for now, or like this statement for now, and maybe I'll talk about this a little bit later or in some other part. But overall, it's much more GC friendly than other versions of iComputed, like computed abstractions. and it allows you to create its remote replicas. The next part will be about this. Yeah, basically that's it. So let's try to run some code, and let's basically create a console app where I'm going to run the code. By the way, again, just to make it clear, when you run the tutorial, you can actually run the code right here, and you can modify it here and run it right in the tutorial. It uses try.net. It's a great tool, and but nevertheless, I think for the sake of clarity, we are going to repeat this exercise using a separate app. So we have programs, yes, here. We will just copy paste code, and this thing is going to be here. Wait. Um, come on. Please import all the references. Okay. It can't because, sorry, because we didn't add Fusion. I forgot to do that. Okay. So now import all the references. Let's start using so okay, and as I explained previously, so this attribute is not necessary. You can add it. Basically, you can do this registration manually. This service. Okay, so let's copy paste the code we just tried to run here and run it. Okay. Okay, so what do we see here? We basically create a service here, and then we try to. So earlier you saw that like these methods, they produce regular output, and basically if it said that it's a task of integer, then the method should output a task of integer. But behind the scenes, proxies and Fusion proxy is generated for this service, and this proxy operates with another kind of value which backs this computation. And this value is exactly I computed of int. If you look at this type, right, it's I computed of int. So you can't get it by simply calling this method, but you can capture it using this syntax. And once captured, you can do various fancy things with it. But ultimately, like you see that it shows, let's run. Let me zoom here as well. So, what's this stuff? So you see that like this line is this. And it says that like that's basically a computed of wait, what's this? A computed that describes this computation, and this is its version, and this is its state. So and yeah, finally we can also check a shortcut is consistent. It basically checks that the state is consistent and print its value. So let me control click on is consistent. Basically, there is a number of such shortcuts for, yeah, there are 3 states: computing, consistent, invalidated. And an interface describes something that has a consistency state, and there is a bunch of extension methods for this interface. Usually you need just one is consistent, but maybe this will be handy for you. So what else can we do with, and by the way, so we basically saw all this stuff so far, right? And you notice that there is a consistency state that is computing while this function runs. We can, by the way, there is no example on this in manual, but let's check it. So we can do the following. We can add another line here. Right. So this line will capture the current computed, and you see that while this method runs, its state is computing. But once it's completed, it will be in consistent state, and that's what you see here, right? Okay. What's next? So this is a fancy stuff, and basically, iComputed is seemingly a complex thing that in reality is not that complex. Let me show you why. So I want to click on iComputed, and this is the definition of interesting why it's decompiled. It should be, but anyway, let's move on for now. But yeah, it should be source code, so it's a little bit weird. But as you see, like if you look at what's new there in comparison to other interfaces, basically there is just a single property called output and a few methods like try set out, update async, use async. That's it. The crucial or like the most important part is here. It's untyped version of computed, and basically you see that it has options, input, output type, and iResult output, version, invalidated event, and so on. But interestingly, it also implements this thing, iResult of t, and iResult is an abstraction describing result of a computation. It's basically either value, or if you, so that's an untyped version of this interface, and I think it kind of perfectly shows what it is. It's either a value, and this one always throws an exception if an error, or it's an error. So, and value is supposed to throw an exception when error is set. Unsafe value returns either value or default, in this case, null, right? But here, unsafe value is of type T, so it returns default in case there is an error. Overall, it supports a number of operations like deconstructor and isValue. And there is a type called result of T. So interestingly, I think by some reason, this thing doesn't open interfaces, I mean the source code of interfaces, because the code is like actually in this file and it's available, right? So if you go to result, a struct that implements this iResult of T, and basically it's the implementation of iResult of T that's most frequently used. And you can see how it works. Like, let's say if you check out how value works, and basically it throws an error, right? Otherwise it returns unsafe value. So anyway, interestingly, I computed of T-out implements a result of T-out. So basically it mimics its behavior, and the rest of it are like basically this thing describes the computation itself to which the computed is kind of attached. So all computed instances will, that are mapped to the same computation will have the same computation, or like same in terms of equality. What else? And yeah, the rest of properties are kind of more or less straightforward. So let's move on and let's see what else is there. Basically, tutorial explains that, well, it explains all of these properties that it implements result of T. And interestingly, by the way, it also, there is an interface called a computed impl. Let me show it as well. Okay, let me do a tree. So I don't know writer by some reason can't like find it in search. You know, oh, okay, I need to click this one, right? Computed of. So I need this one. And this is an interface you are not supposed to use normally, but basically what's important about this interface is that it shows that it provides an API that allows to track dependencies for the computed instance and basically add what's used, so there is a number of methods, and since normally you don't need it, I basically just want to show that there is an API allowing you to add dependencies manually. Okay, so let me replace this back to Bart and see what else is there. So as you might guess, any computed instance eventually become invalidated, and invalidate is the method that turns it into this state. Let's actually take this, right? And by the way, earlier you saw, right, that when we invalidate a computed value that kind of sits behind some computation, and this computation will run again. So if we call this method second time here, you will, oh wait, forgot, right. And you will see the output, but you see that get async A was not printed, even though like this method prints this thing, right? But interestingly, if you validate the computer, so now you see that it's printed because the proxy that backs this method, it actually found out that the computer that's cached for the specific computation is invalidated, so it can be used. And that's why the computation just happened. Okay. So there's a bunch of diagrams here. It basically summarizes all that I said about the structure of I computed. This one shows possible state transitions for consistency state. Basically, they are born in computing state and either they immediately enter invalidated state, or they get into consistent state and then get to invalidated state. And eventually, like if you dereference a computed value, then it will be collected by garbage collector. And by the way, the cache, or like whatever caches all these instances, it's like in reality it's a weak reference based cache, like GC handle actually based cache. So it actually reliably tracks only what's used, and like what's unused, unreferenced. It's basically it's going to stay there, and there are options for that, but not indefinitely. And you like I'll explain this, I guess, in the next part, or maybe a little bit later. But anyway, and here is an animation that shows what actually happens with computed instances when you recompute something complex. So let's wait when it kind of restarts. Basically, that's the dependency graph you have at some point, right? And then one of deep dependencies was invalidated. So whatever is dependent on it was invalidated. But like for this dependency, we have something like, let's say, live state or something similar that eventually recomputes it. And as you see during the recomputation, this whole thing, basically a set of new computed values was built, and like they were kind of, they replaced the dead part of the graph. So that's nearly how it works. Okay, let's move on and see what else do we have here. And there is another sample. Let me again copy this one. And okay, so this one just shows that, let me run it first. So this one shows that every computed instance actually knows how to recompute itself. And that's the way it actually recomputes itself, update async method. So once you call update async, you get a new computed that describes the most current result of the computation. It's not necessarily going to be consistent as it's shown here, because it could be invalidated, let's say, right, I don't know, you do, and then you, sorry, I think it's clear that it could be invalidated between these two lines, right? And so, but nevertheless, it's the most current value. And I guess if you have one, and you at least may assume that recently it was the current value. Anyway, and interestingly, so this animation uses renew async name of as a name of the method, but yeah, later it was renamed to update async. So let's run another step. And what do we have here? Oh, so this one shows that, in fact, so it produces the same output, but you may notice that it's like almost exactly this code. The only difference is that this line was changed with this line. And basically, if you look at what invalidate method does, you will see that in reality, it okay, it's not actually exactly as like you may think of it, as if it actually captures the computed value and then invalidates it. But it's not quite correct, because capturing means it could be created during the computation, but invalidation happens for cached values only. So basically, there is a little bit different construction that ensures that, like, if there is nothing to invalidate, then there will be no invalidation. And that's kind of correct way of doing this. And similarly, another line basically just runs the computation differently, but like it's in fact the same as this thing. So, okay. And okay, let's get to, I guess it's final example here, right? Let's get to the final example. And probably the most interesting one, it shows that it's fairly easy to, so if you have, if you know when computed instance it gets invalidated, right, then you also can update it right after that. And this is exactly what happens here. So we get the same service and we basically run a background task that will increment the counter every second here, right? So basically a delay and increment, right? And then we get a counter for the same value, 8, right? And we start writing a value of computed, but like in the loop, we do the following. We wait when it gets invalidated, get a new computed instance by updating it, and prints it. So let's see the output. So if you will look at the second part of the time here, I mean the seconds part of the time here, we'll notice that basically every second the counter gets a bump, and this is the logic that's happening in another thread that basically triggers the counter increment, and the logic in main thread kind of notices this. So this is actually what you need to have real-time updates and to build real-time applications. And I think this is the first example in this tutorial that kind of shows you can basically recompute a huge state when one of its small pieces or parts change. And it's up to you like when to recompute, but you will instantly learn that like you have to recompute it. So I don't think there is way more here. And I think the last question that's kind of answered here is, so why Fusion uses this interesting kind of, or like why it differs, why its I computed abstraction has invalidation concept. And so it's explained here. Basically, Knockout and Mobex, they are built to power client-side models, which are tiny. And Fusion is built to power server-side models, which are huge. Basically, that's all the data you have. And with such models, you can't afford to recompute everything when a small piece changes. What you can afford though is to like recompute everything when you really need it. And it's still better than like, let's say, as so think what you do in a regular app, right? When you don't have all of this fancy stuff, you normally just pull the data again from, let's say, database or like different storages, and unless you have a fairly sophisticated caching logic, you usually just kind of recompute everything when you need to compute something. So Fusion eliminates this kind of necessity to recompute everything. You will be recomputing just the stuff that's not computed and not kind of used right now by something else. But like, basically that's the reason this approach works. So on one hand, you kind of just keeping, sorry, let me kind of rephrase it. So earlier I told that Fusion is built to power huge models, right? And but how, right? How it can do that if these models don't fit in memory? So interestingly, you don't have to fit the whole model in memory. What you need to fit in memory is basically the dependency graph for values that you observe, right? Basically, if you observe something and want to know when it changed, then you need to know about all the dependencies of this thing, so that if one of these dependencies change, then like this thing propagates to the value you observe and invalidates it. And if you think about this, like let's say, think about, I don't know, any app with UI. Usually what you present in UI is only a fairly small amount of data. So even if you trace down all of these dependencies, it's still going to be basically sort of one or like a limited set of data. And this is what you can fit in memory. And Fusion will make sure that basically all these dependencies are traced, and when one of these dependencies gets invalidated, like you will get an invalidation notification, and then you will be able to recompute either the whole thing or a part of it. It's up to you. So this is why I guess the abstraction Fusion uses is very different. It's designed for on-demand recomputation, but not like immediate recomputation. I guess it's worth reading this part as well. It explains like how it helps to scale the app you or the craft with it. And I guess that's it. Thanks for watching another video on Fusion tutorial. See you next time.